All right, what do I see in the chat box here? I want to make sure that, okay. Michael, you hear everything okay now? Okay, good. Hopefully, we're good to go now. This is Roger, and appreciate everybody taking time out to go through this newly revised version of this particular presentation. I'd like to make sure though that everybody is can hear okay. So if you would please just and this is practicing finding the hand raise button on your screen anyway. Just raise your hand as well if you can hear me. I should say raise your hand if you can't hear me, but maybe that wouldn't quite get the same results. Okay, looks like we're good to go here. Thank you, everybody. Okay, well, let's get started. This is kind of a long presentation. There's 59 slides, so I got to kind of guide it, try to make sure we don't do more than 2 minutes on any one slide. And just a reminder that the slides are available to you. You're free to use them as you wish. Just get with the host at the end of the program, and he'd be happy to supply you with the slides. And that'll help. Maybe you already have them, but if you don't, they also help with the quiz to go through the slides again. Okay, so is PV still too expensive? There's one slide. Did that one in 5 seconds. That's not too bad. Well, here's a chart of right on up to 2024. And if 25 cents a watt is too expensive, then maybe it's still too expensive, but we're going to look at some other ways of evaluating whether PV is still expensive. What's interesting here is the fact that the cost has come down by a factor of 500 since 1976. Now, you might ask about these costs. Depending on where you look and depending on the quality and the efficiency of the module itself, 25 cents is kind of a ballpark figure because some are going to be more expensive. We pay a bit more here in South Florida because it's pretty windy, and withstanding 175-mile-an-hour wind on your design guidelines means you have to have a pretty good frame, and also if you are willing to pay for a less efficient module, you get it for less cost. But if you want to get as many watts as possible on your roof, then you pay a little bit for the module. So anyway, things are getting less expensive, bottom line. These are numbers you just pick out of what they used to cost. You can correct for inflation. That would probably say that they're not quite that much. Well, whatever it says, because you have to make a lot of assumptions. And in any case, this is what you're paying out of your pocket right now, less whatever rebates or incentive there might be. So the way that the industry normally compares prices of electricity these days is the levelized cost of electricity. And so if we look at various electric sources, what we see is if we have combined cycle dispatchable power, that's basically a natural gas kind of a system where it's predictable. Dispatchable and predictable kind of go hand in hand. You can install that, and if you charge 3.75 cents a kilowatt hour over the life of the system, you'll break even. And that's what LCOE stands for. What do you have to charge for electricity in order to pay for your investment by the time your investment is ready to be disposed of? And that includes the disposal costs as well. If we look at onshore wind, that's at 3.78 cents. These are all from the United States Energy Information Administration, by the way. Standalone photovoltaics. This is an average over the utility scale plus rooftop type scale. That's 3.35 cents a kilowatt hour. And if you were to do just utility scale, it would be less than that. And if you were to do just rooftop solar, it would be more than that. A hybrid PV that includes energy storage gets up to about 5.47 cents a kilowatt hour. And residential PV, I ran this myself just a few days ago, looking at some of the prices that are out there, and a reasonable number for a residential PV now is 6 cents a kilowatt hour, just to compare it with other energy sources. So bottom line is a lot of people are taking advantage of this because it they in general, I don't know of any utilities out there that are charging less than 6 cents a kilowatt hour for their electricity. So people who have roof space in general are taking advantage of it. And even geothermal is where it's available is running at somewhere in the neighborhood about almost the same as the other sources on top, the wind and the PV. So there's a fair amount of various renewable energy sources out there at reasonable prices to the consumer and to the builder. And that's why Wall Street is starting to become pretty interested in this stuff. So let's learn how to install some of these things. The asterisk is, oh, by the way, 2027. This is the installed cost assumed for sources, some of which the planning will start now, the larger systems. So this is 2027 cost. We don't know that for sure, but that's the estimated cost based on projections of the cost of everything that's involved in going into these resources. I thought it'd be interesting because now everybody in 3 years can take a look and see how accurate this projection was. Actually, you don't need to wait 3 years because in order to have them in operation by 2027, we're going to have to start building them now and start thinking about them now. Okay, so anyway, another way of looking at photovoltaics as to whether it's worth it is the energy return on investment. In other words, what's the payback period for them? How long does it take for the cell to pay for the energy, for the cell to produce as much energy as was used in its manufacture in the first place? And here we're talking about the system. Clearly, the cell can't just do that all by itself. It has to be connected by way of inverters and other things that we'll talk about. And right now in 2024, if you look all over the place, depending on system, depending on a lot of variables, depending on, for that matter, where you are and what direction the array is looking, because that is going to determine how many kilowatt hours it's going to make in a year. So the energy payback time is about 3 years. The energy return on investment over the life of the system is making somewhere on average here, a weighted average, whatever you want to call it, is somewhere around 20 times as much electricity that was used in manufacturing it is being returned to the system by the solar system itself. So that's pretty good energy return on investment. There aren't very many sources that have that good. So even this is a good number to be looking at. One reason prices are coming down is because the energy return on investment is getting better. Production of cells and modules is getting more efficient. Cells themselves are more efficient. Everything's going in the right direction right now, and folks on Wall Street are noticing that, and they're starting to put their money where their mouth is, or maybe where our mouths are, or whatever. So bottom line is the inverters and the other parts of the system as well are are becoming less expensive. They're a part of this electronics industry where TV sets were $1,500 10 years ago, and they're $500 now for the same thing. A lot different than almond milk or certain groceries that are going up like crazy. So let's see if we can come on and see what we can learn about them. We probably have some people, and depending on how time goes, I'm going to want us to have some discussion, see if any of the folks in the group here are in the solar business or energy storage business or whatever. But I want to get through as far as we can. First, if you do have a question, feel free to type it into the Q&A box, because they will see that. If you have an administrative issue, something doesn't come through or whatever, do that in the chat box, and that way our host will read anything that comes up in the chat box, and I will watch for notifications from the Q&A box and try to respond to them as soon as possible. You're entitled to ask questions. That's part of the cost of the program this afternoon, so don't hesitate. One kind of system is standalone system. It means it makes its electricity, it stores its electricity, uses it when it needs it. You might imagine where this system is with the tilt on those modules. A pretty steep tilt. And as a matter of fact, it's in Alaska. Folks might think, gosh, Alaska, photovoltaics, maybe some other sources, like geothermal. But in any case, if you go to Alaska, you will see PV up there. And the standalone is simply one that's not tied into the grid. The other one is the one that's connected to the grid. And anybody who's up in the northern New York may have seen this at the in Tupper Lake at the Nature Center there. This has been there for quite a while. It's one of the more creative applications that I've seen on that curved roof. And that's a big system for back when that was first installed. But I like the picture, so I decided I'm not going to update that. That's some newer picture that just shows that PV's been around for a while. So a few more examples. Here's a standalone system out in Nevada at the entrance to a national park. Here's a standalone system in Utah, a little weather station. Here's a Wyoming standalone system, big game crossing. And you better wait for at least 5 miles. You have to watch out what you're doing, or you never know what you might run into. So these are all standalone systems. If we take a ride up to Massachusetts, you might see some systems like this on roofs. These, of course, are grid connected. And if you go up to Yellowknife, Northwest Territories, Canada, you might see something that looks like this. And they're tilted a little bit higher tilt. And these have been there for a while. But the house, and you see that this is a utility interactive type system. You can see the utility coming in from the left-hand side there. So this is, I don't remember when I took this, 10 years ago, something like that. Commercial rooftop systems, utility scale systems. So just there's a lot of stuff out there already, and it's growing faster and faster and faster, as we've noted at the beginning. So let's get some background. The field is changing so fast, and particularly now software and artificial intelligence and other things are getting involved, with lots of current sensors being used and things for load limiting and load management, that it's really important to understand the background of all this stuff. So when the manufacturer changes their installation manual instructions once every month, or maybe more frequently, you'll understand why they did what they did. So that's the goal today, is to give you a good overall understanding of the installation of a photovoltaic system. This will be residential type systems for the most part. And the whole idea is to get the whole theory behind stuff so that when you read the data sheets and when you read the installation manuals, the words you see there will have some meaning to you. You can say, oh, I saw it in that June 5th webinar. I know what that is. All right, so that's your goal today, is to understand how these things work and what the design engineers go through in order to make sure the customer is happy, the utility is happy, and everybody's happy. Okay, now, a little information on the sun. The peak sun intensity at the surface of the Earth is roughly 1,000 watts per square meter. Instead of, we might have talked about foot candles and all kinds of things if we had a photography show here. But we're talking about energy and gathering energy and collecting it, so it's nice to know what's out there and available. So every square meter of surface, if the sun is shining directly on it, the most energy you can collect from that is about 1,000 watts per square meter. So don't believe any of these ads you see that say we will focus on and we will give you more than 1,000 watts per square meter. Yeah, but they're collecting it for more than 1 square meter and concentrating it on a smaller area. But the sun itself, what we get at the at ground level is about 1,000 watts per square meter, unless you're up high in the mountains where the atmosphere is less, because in fact the sun intensity at the top of the atmosphere is about 1,300 and some watts per square meter, and so about a third of it actually gets absorbed or reflected back by the time it gets down to the Earth's surface. So that's nice that we know about 1,000 watts per square meter, and then we look at how much of that can we capture. And that depends on the technology. And with the most common technology right now, which is about 95% is crystalline silicon, the amount that it's capturing is in the 20 to 22% range. And it's that low because this is what you can do with silicon. There are theoretical limits to everything based on thermodynamics and lots of other things. But basically, it's a matter of when the sun shines on the panel, is it going to convert it to electricity or to heat? And of course, it's going to convert it to some combination of the two. And it's the question of whether you get 5% reflected, 20% converted to electricity, and 75% of it becomes heat, which then has to be re-radiated away. But as long as we know about that, then we just design according to knowing that, just as they design a coal plant or an oil plant, knowing they're losing a lot to heat on that as well. Okay, the annual conversion range is about a 1,000 to 2,000 kilowatt hours per kilowatt per year. All right, and this depends on a lot of things. If you're pointing north, if you're pointing west, south, tilted at latitude, whatever, the range is quite pretty large. You maybe have a module facing north that will collect about 60% of what a module facing south might collect. But then again, sometimes 60%, if you do the levelized cost of electricity on that, even that comes out pretty favorable in certain areas. And here in Florida, we see a fair amount of north pointing or north facing rooftop installations these days. If that's the only roof you have that's not shaded by trees, then it's about the best you do, and you have to put more solar on your roof to get the same amount of electricity. And it costs more, and so your levelized cost of electricity for that kind of a system might jump up to 8 cents. But even 8 cents is not that unattractive. So there are models that you can access from places like the National Renewable Energy Labs that has the so-called SAM, Solar Advisory model, and it's free and it's fun and it's intuitive one of the best intuitive things I've seen. And all you have to do is log in to National Renewable Energy Labs and ask it to please give you a free copy of SAM, System Advisory Model, but they'll probably call it SAM. And then you can, instead if you get bored with TV after dinner, you can model how much your solar system would produce if it's looking at 195 degrees and at a tilt of 20 degrees and wherever you might live. And it'll tell you exactly what you should expect. Of course, that's weather contingent, and that's to believe that we're going to have the same weather every day of every year. No, don't kid yourself, but still, on an annual basis, the predictions are pretty good. Okay, so there's the sun. That's where we start. And then we have to do something with it. And we have to collect it. And it's interesting to look at the collection curves for the modules. And here we have a module that it's rated at about, well, let's see, how do you get the rating? You have to multiply the current times the voltage, okay? Let's look at the curve at the top. That's what the module will do at 1,000 watts per square meter. And you notice that if there's 0 volts, will produce about 11 point something or other amperes. But that's fine if it produces 11 amps, but that's no power at 0 volts. In other words, you can short the thing out and it will be current limited to 11.5 amps. So it's not going to blow up anything. If you move out, say though, to 30 volts, you're still getting almost that same 11.5 amps, let's say 11 amps. So now at 30 volts and 11 amps, there's 330 watts. And that's something that you don't, that's something to start thinking about. And when you move out there to 40 volts, you're still getting over 11 amps. So like that's 400 watts almost. And when you get out to that little black dot up there, it's labeled VM and IM. That's your maximum power point for the module. And for this particular module, it looks like we're going to get about 440 to 450 watts. And this is a fairly common size these days. And of course, if you keep going up, if the voltage goes up, then all of a sudden you get lots of volts, but no amps and still no power. And of course, that's your so-called open circuit voltage condition. And that's why you got to protect yourself from the terminals of these modules if you're working with them. And fortunately, they have connectors that are designed with safety in mind. And if you touch the end of the connector, it's still insulated so that you can't get a nasty shock with these connectors that you connect them with. So this is current versus voltage. But since the maximum power points are so important, we've got a number of different ways we characterize these modules. They have a short circuit current, open circuit voltage, and maximum power current and maximum power voltage. That's that one up there in the corner that is labeled. When we look at the module power versus voltage, which is maybe a little more useful because it says, wow, okay, this tells us where we want to operate them. Clearly, we want to take advantage of full power. How do we do that? Well, fortunately, electronically, it's very straightforward to build a device that will track the maximum power point of the module. And guess what that might be called? Believe it or not, that is called a maximum power point tracker. Now, these maximum power points, these are nice, and it would be nice if this was all there was to it, except there's a little more thing that we need to pay attention to. Pretty much all solar that you get now has maximum power point tracking. And I mean, you can buy some that doesn't, but for the most part, the folks who make maximum power point trackers want their product to sell, so they make it sufficiently economically attractive that it earns its, you get the investment money back from it in a pretty short time, a couple of years at most. So the charge controller and almost every single grid connected inverter you ever lay your hands on, they're going to have built-in maximum power point tracking. And we're going to talk about a number of different kinds as we go on here. Okay. But the other thing we need to remember is that as the modules get hotter, they produce less power. The test temperature where these are rated at is 25 degrees C. And you can see this particular module at 25 C has a maximum point up here right around 440 watts. Whereas if we could cool it down to 0, it will put out almost 500 watts. But in reality, the temperature of that module, given that 20% was converted of the sunlight is converted to electricity, and about 75% is converted to heat, that module is very likely going to be operating at a temperature in the range of 130, 140 degrees C. And if it gets up that hot, not 100, that's 130, 140 Fahrenheit. But if it gets up to 50 degrees Celsius, and it could get as high as 75, then you're looking at power reductions of somewhere up to almost 15%. And that's why it's buying a system based on its rating in watts is good. But what's better is to convert how many kilowatt hours a year will that watts make, because most of that, those kilowatt hours are going to be made at a power level less. However, the power level less is going to depend on the maximum power rating of the module. And the higher the maximum power rating of the module, the more power it will deliver at a given illumination level and temperature. So just some practical things that we are useful to know about these modules. Note that the maximum power decrease is in the neighborhood of 0.3% per degree C. And as a result, you do what you can to keep them kind of cool. And that's why, one reason why the modules themselves are generally raised about 6 inches up off the roof and mounted parallel to the roof. All those systems you saw earlier. And that's a little bit of air get behind them. And that tends to cool them off a little bit. And given that the module itself intercepts that radiation from the sun at 1,000 watts per square meter, or even say 800, whatever, and 75% converts to heat, of that 75%, about half of it is transferred to the roof and the other half gets reflected upward or re-radiated upward. So you're cutting down the exposure of the roof to the sun by about a factor of slightly more than 2. So if you only get half as much sun on your roof, that means it's going to last a little bit longer. A lot of people don't think of that, but the fact of the matter is the roof under the modules lasts a little bit longer. And furthermore, if you're screwing these things down to the roof with 4-inch lag screws, that's a whole lot more strength than nailing down your roof decking with roofing nails. So when you talk about getting into a hurricane, it's the roofs that have the modules mounted securely to the roof that also mount the roof securely to the rafters. And as long as the rafters are securely mounted to the frame of the house, chances are you're not going to lose your roof. And they've done a lot of photos out there, a lot of aerial photos of the damage after a hurricane. And it's amazing how the houses with the PV on their roofs generally have roofs with much less damage. So that had nothing to do with module power versus temperature, but it's an interesting observation. Let's say you're in Albany and you want to, it's not convenient for you to mount a solar array facing south. You maybe have to face southwest. Well, it turns out that in Albany, your best orientation of a fixed solar collector is at a 30-degree tilt facing south. That's where you get 100% of the annual maximum solar collection. But if you happen to have to face southeast, you still can get 95% of it if you're at a 25-degree tilt. Southeast 40 degrees, 94% of the maximum. North, 71%. So even at a 15-degree tilt on a north-facing roof, you're still getting essentially 70% of what you would get with the optimum mounting. And so this is something that not everybody necessarily knows or doesn't necessarily know specifically what the numbers are. But this is based on simulating using National Renewable Energy Lab STEM. And you can do this for wherever you might happen to be watching the program. Here today, watching the program, we're not on TV, this is the internet. So anyway, whatever. And you can do this for your place and see what your capacities are for various orientations of arrays. All right, so we want to tie into the grid. That's what most systems since the year 2000 have been grid connected. And there's reasons for that, because when you're not using the electricity, somebody else can use it. And you don't have to have a battery to keep it, although it's nice to have batteries. We'll get into that in another, but we're not going to get into battery storage in this particular presentation. Okay, so what are the grid connected options? Well, straight grid connect. In other words, make your electricity connected to the grid by way of maybe a backfed circuit breaker in your main distribution panel. All right. So it makes electricity when the sun shines and the grid is connected. It sends electricity to whatever loads you want. And if there's any left over, it goes back to the grid, provided the grid is up. But if the grid goes down, then your system has to go down, because otherwise it would be sending electricity back to the grid, maybe when somebody is trying to repair a 12,000 volt distribution line. And solar electricity can make 12,000 volts backfed through a transformer just as well as any other kind of electricity, and it has the same effect on a person who inadvertently gets in contact with it. So therefore, it's pretty important. And the rules are that if you have a straight grid connect inverter, if the grid goes down completely, it has to disconnect from the grid within 2 seconds. And I think they arrived at that number because no utility has ever been able to respond to an outage in less than 2 seconds. So anyway, this is that's our story on the grid connect. If we have a battery backup grid connect, which we're not going to go into today, they have got all the features of straight grid connect, but they also have standby circuits that can be powered by the solar and by the batteries when the grid is down. And the batteries can be charged either by the solar or by the utility or both, depending on who's available at the time. And the most recent version of IEEE 1547-2018 says that it is possible for an owner of a photovoltaic system to sign an agreement with the utility to allow the utility to control their system to buy electricity during utility peak time, when the utility maybe needs it. And furthermore, if you've got battery backup, then not only can you buy or sell your electricity to the utility at peak time, but you can buy it from the utility when they have excess, like when the nukes are running at night. If you buy that electricity, the excess electricity, then they don't have to throttle back their other generation. So some really, really interesting stuff going on these days, the bottom line. And like I say, a lot of it is involves software and communication and other things, and yeah, it requires special purpose hardware, of course, and they're able to do that. So let's see, how are we doing on time? Let's take a quick look. We're okay. So, what do we expect from a properly designed and installed photovoltaic system? Well, for one thing, it should meet the electrical design performance specs. It's very disappointing when you don't get as much electricity as you're hoping for. Then you got to go figure out, what do we do wrong? It's really nice if it doesn't leak if it's on a roof, and in fact, if it prevents the roof from leaking, that's even better. And in some cases, that's what's going to happen, because if you take a look at the way these attachments are sealed, it looks as though they wouldn't leak for 100 years almost. I'm not sure whether that's true, but I've have acquaintances one way or another with quite a few installers, and I've never heard anybody fussing about having to go out and fix more leaks. So apparently, a roof doesn't leak anymore with a properly installed solar system than it's going to leak anyway if it gets too old. Okay, it's really nice that it doesn't blow away. And as I just mentioned, a lot of times the roof is actually more secure with a properly mounted system. And it should look nice. And of course, beauty is in the eye of the beholder. If you've got a solar system that works when the utility is down, and you've got hot coffee and cold beer and hot showers, and your neighbors don't, then all of a sudden your solar system looks pretty good. So it also should last 25 years or more with minimum degradation, because that's the most modules are warranted to produce somewhere in the neighborhood of 85% of the power they started with at year 0 by the time they reach year 25. And there are now other parts of the system are generally also designed to last for that 25 years. So inverters, whatever, some inverters you can extend the warranty to 25, but if you use a microinverter, you buy it off the shelf with a 25-year warranty. And we're going to talk about microinverters very soon. And the properly designed system should be able to help the utility at a time when they need electricity. Most systems are still putting out some electricity at 4 in the afternoon. And the utility sometimes can use that to its advantage if it needs some extra electricity. There are going to be a lot of other things happening, load management and so forth. That's already been happening. It's going to be happening even more, but that's a subject of another presentation. So what are we going to need then for the system? Well, you're going to need modules, okay? I'm pretty sure everybody has seen PV modules now. Pretty hard to drive around and not see a system somewhere. Even ride the Long Island Railroad train, you see PV systems alongside the tracks. So you need the modules. You need some way to support the modules. You need a proper method for mounting these various supports. You need an inverter that's properly listed to make good AC electricity. You need code compliant disconnects and wiring. You need code compliant utility connections. You need a rapid shutdown provision so that if a utility wants to make sure that none of that electricity from the solar system is accessible to the firefighters or any other emergency responder, you need a switch you can flip and it shuts everything down. And there's no electricity that leaves the boundary of the solar system on the roof. You need a permit, unless you're way back in the woods someplace doing a non-grid connected system. But otherwise, you're going to have to get a permit. That's fun. Generally takes about as long to get a permit as to get the thing designed. Maybe longer, depends. And you're going to have to sign an agreement with the utility that if they want to turn off your system for whatever reason, they can come and do that. But otherwise, they will pay you a certain amount for whatever electricity is delivered to them upon being connected. So that's what, the leading up to the installation. These are things that you need to be accumulating and getting straightened out. Okay, now we talk about straight grid connect systems. And we talked about two types of systems. One is grid connected and one is not grid connected. But when you grid connect, there's two ways to do that too. One is to use string fed inverters. Actually, there's three ways, I'm sorry. And this is a rough diagram of a string fed inverter. And you notice that the modules are connected in series. At least, well, yeah, everybody will notice because all engineers have to take circuits one. So you can see that the plus on one is connected to the minus of the next one and so on. And then it's returned back into that junction box thing. Okay, so a typical string fed inverter, that means that every module in that system has to run at the very same current. And therefore, in order for every module to produce the very same current, every one would have to be the same model that performs exactly identical to the one next to it. That when the sun shines on a certain intensity will produce exactly the same current. But if one of those modules gets shaded, then that one module's not going to want to produce that much current, no matter what you do with it. So what it's going to do, it is going to hold up the whole string, and everything else, the total current it can produce is going to be limited by that one shaded module. So with a string fed inverter, you want to be really careful how you lay those modules out, because you don't want every module and even one of those modules and one of those strings to be shaded, because that will in fact affect the performance of the entire system. Now notice that the two strings are connected in parallel. And that means that the overall strings have to be operating at the very same voltage, which means that in general, those strings would have to be identical and facing the same direction and so forth in order to track their maximum power points, unless the inverter itself has inputs which can accommodate different strings as different maximum power points on a string level basis. Okay, so that's the key on a straight grid connect system. They're the least expensive because they don't have any fancy stuff to make sure that every module is getting the most from the sun it possibly can gather. Okay, from the inverter, it's got an AC disconnect, goes to a distribution panel probably, but there are other ways as well that we'll explore. And that's where it's tied into the utility. And of course, the occupancy gets first choice at that electricity, and anything the occupancy doesn't use will be delivered back to the utility. The other thing to consider is in their operational mode, these modules are normally considered to operate, well, in the inverter itself is designed to operate as a current source. So it is synchronized by the utility voltage, and it delivers current in phase with that voltage or out of phase if the utility requests that it be delivered out of phase. But the utility voltage is a key here for the proper synchronization of the current to produce real power. Okay, so the other kind of system is a microinverter system. And these are really popular these days. The reason is because each module has its very own inverter. And that means every module operates independently of all of the other modules. The connections you notice now, there's two wires going up there to each inverter, and these inverters are connected in parallel. And what do you connect in parallel? You connect current sources in parallel. And the current from each module is delivered at the very same voltage of 240 or 208 or whatever the grid voltage is, because again, the grid voltage is synchronizing the inverter And if the grid voltage is lost, the inverter shuts off, except for certain situations that we talk about later. But in general, the inverter, if it loses synchronization from the utility, then it shuts off. So, but these microinverters, most of them are warranted for 25 years, same life as the modules themselves. So it's an interesting system, costs a little bit more, but amazingly reliable. And given a residential roof and all the strange orientations of the roof, plus surrounding things that might shade, it's generally a pretty good investment. So, and a goodly number of those, that's predominantly the type of installation here in South Florida and in a lot of other places. So the currency, each of these strings is combined. They all are the outputs all of every string are carried on down to the combiner. So here you'd have 4 wires plus a ground coming down to the combiner, where the outputs of the 2 strings are combined together. So if you got 12 amps and 10 amps, you get 22 amps at the output of the combiner. Okay, and then it goes to a disconnect. And if you turn off the disconnect, then all those microinverters think the utility's gone away and they shut off. Then it's connected to the utility through the distribution panel, and that's the system. Another system is an optimizer system that takes advantage of a couple things. One is that it operates at a relatively higher DC voltage at the end of the string. For residential, typically around 400 volts. For commercial, typically around 850 volts. And the advantage of that is you have less power loss in the connection between the roof and the inverter. So, and you've got DC coming down from the roof rather than AC. Notice these are connected in series in order to get a high voltage in the neighborhood of 400 volts. We're going to design one of these later. There's 3 different types, and we're going to make every effort to make it through and design one of each of them. So let's see. That means we better design pretty fast. So we're going to start with mounting, and I'm going to go through this relatively quickly, and anybody that's interested, make sure you order up a set of slides. And there's a lot of math in here, so you can go through and see. And there are a lot of references to ASCE 7-22. That's the American Society of Civil Engineers. They have made great progress in empirical data-driven formulations for exactly how you make sure these things don't blow away. So in other words, calculating the wind load is what we're going to be doing here. Sorry, I gotta press the right number here. There it is. I turned off that. Sorry about that. Okay, so we're going to look at some structural design considerations rather quickly, just to give you an appreciation. And I'm sure the civils and the mechanicals will appreciate it more than the electricals in the group. Maybe the electricals will appreciate the value of civil and mechanical engineering, though, because this is pretty interesting stuff. And this is spoken by an electrical engineer who's just spent a fair amount of time recently looking through the latest edition of the Civil Engineering Handbook on structural integrity. Okay, so usually design starts with the module, but sometimes there's other reasons. But in any case, you got to have modules. So first thing is need to be listed. Used to be UL 1703 would do the job, but the 61730 has gone into the international scene since modules are made all over the planet now. And so folks have gotten together and agreed that if you list it to UL 61730 is actually a copy of an international standard. And if it's listed to that standard, it means it's pretty quality stuff. And that's like a UL listing of almost anything. It's highly likely that you need to have a UL listed or you're not going to be allowed to install it, whether it's an air conditioner or whatever it is. So In addition to those electrical properties we talked about that modules have, they have thermal properties, and they also have structural properties. And the structural properties get pretty important, and that's what UL 1703 is about. You have to have minimum resistance to wind and other earthquakes and whatever. So let's take a look. Let's pick a module. Here's a fairly typical one. It's a little bit older than the ones in usual, but the process is the same. And when the procedure stays the same, I didn't bother to put in the new one. But 18 square feet is pretty close. The typical module now is probably going to be 21 square feet, so not much of a difference. Going to have that 1703 listing. And in order to get that listing, it's going to have 5.4 kilonewton square meters downward, and probably can withstand about 75 pounds per square foot upward. Now, there's some that will withstand the full 113 upward and downward both. That's where I say the quality of the module and the strengthening will make a difference in the cost of the module, but sometimes wherever you live may require that you spend a little extra to make sure the thing doesn't blow away. But you'll generally get a reward for that. Now, once you've got that module, then you need to decide where you're going to put it. And if you look at ASCE 722, there are lots and lots and lots of diagrams in that document. And what it'll show you is that the zone on a roof, and the roof zone means what kind of wind pressures are present at different parts of the roof. And certain zones have more pressure than other zones. All right, and that depends on a lot of things, like the type of roof, the slope of the roof, and the dimensions of the building. Generally, it looks something like this. Zone 1 is kind of inside protected and subjected to the least wind load. Zone 2 is at the edge of the roof and tends to be a little bit higher pressure. And zone 3 is, depending on the roof, whether it's a gable roof or whether it's a hip roof, zone 3 might be across the bottom. It might be just at the corners. And generally in zone 3, that's where the highest pressure is. And interestingly enough, the highest pressures are uplift pressures. It's like Venturi effect when you are pressing a button on that sprayer, that perfume or whatever. When you blow across the top of something, that suction pressure that's created, you see a convertible driving down the road, and people's hair is going to be blowing towards the front of the car. And that's because of this suction that takes place. And this has been very carefully measured by the ASCE people on rooftops. And these are the results they come up with. Zone boundaries depend on, between zone 1, 2, and 3, depend on this boundary factor A. And it's defined as 10% of the least horizontal dimension, or 0.4H, whichever is smaller but not less than 4% of the least horizontal dimension, or 3 feet, which if you read 10 times, you'll probably figure out exactly what they mean by it. Okay, but it's a boundary. And that's how you determine the boundary between different zones, depends on different things, like the horizontal dimension, the height of the roof, and so forth. So, then you just fit the modules on the roof. And of course, then you don't want to just get a bunch of modules and start screwing them down to the roof and then find out that, oh dear, I should have done this a little differently. It's kind of nice to plan in advance. So you draw your roof up, and it might look like this. And with this particular least horizontal dimension of 35 feet, we get A equals 3.5 feet for that number that we had in the last slide. And so that's our zone boundary in the dotted line. And what we've got is a distance looking straight down at the roof of 18 feet from the eave to the peak. 19 feet across the top. You can tell that this is a hip roof because that's the way hip roofs come together at the corners and the top. And so there's our roof for this example. And since we're just going to do this once, this will be the roof we use for all of our electrical different examples. We'll have just one structural exercise here. But there's our roof. So now what do you do? Well, we got that module, we know its dimensions, so we start adding them onto the roof. And it might look something like this. It might not look like something like this because it is highly likely that there will be a fire code that requires those modules near the top to give either an 18 or 36-inch access for a firefighter at the crown of the roof. So those are problematic up there on top. They may or may not be able to be there. They might be able to be there, maybe 3 of them laying horizontally in the landscape position rather than portrait. But assuming it can be done like this for one reason or another, then we can proceed with the design. We could have proceeded with the design if we had 3 rows, 3 modules lying flat, or not even had that top row for that matter. But we'll do it with this one just to show the procedure. Okay, so first thing we have to determine the wind load. That's fun. These are what things you need to know. You need to know the mean roof height. You need to know the roof zone. You need to know the risk category. You need to know the exposure category. You need to know the escarpment, whether it's on a hill or not. You need to know the size of the module. You need to know the slope of the roof. You need to know the type of the roof. And you need to know how fast the wind is going to blow. That's all you need to know in order to do a wind load calculation. All right, sounds simple, doesn't it? So, what's a risk category? Well, you can look them up in ASCE 722. Category number 1 is structures with low risk to human life. Number 2, structures not specific in 1, 3, or 4. Well, that's nice. That means everything's covered. 3 is structures that could be a substantial risk to human life. And it could produce a substantial economic impact or mass disruption of day-to-day activity or whatever. So what might this be? Well, I mean, if it's an explosive company that manufactures explosives, yeah, that's pretty important. If it's a company that manufactures toxic chemicals, that's pretty important. It's substantial risk to human life doesn't require a whole lot of imagination to figure out what kind of building that might be. And structure number 4 is structures designed as essential facilities, so emergency services, manufacture of fuel, and there's probably some debate whether a hospital would be considered 3 or 4, but in either case, if you read these very carefully, these are summaries of what they say in the ASCE 722. So it's important if you got something non-residential that you read the definitions for category 3 and category 4 very carefully, so you know for sure. Now, clearly a fire station is emergency services. That's going to be number 4. A school, what's that? Okay, well, that's a pretty substantial risk to human life if it blows apart. But one could argue to some extent that if there's a hurricane coming, then nobody's going to be in school anyway. So anyway, read the instructions. It's important to know. Then you calculate the wind load, and there's 3 chapters that relate to wind loads, and a lot of other chapters relating to things like tornadoes, and that's actually a separate chapter, earthquakes, and so on. So each risk category has a different set of wind speed contours. Category 4, you have to design for a higher wind speed than you do for category 1. That's what it boils down to. Because if you design for the higher wind speed, it's less likely that it's going to be damaged by wind. All right, and so after you figure out the design wind speed, then you have to calculate this formula. And what this is the 0.00256 relates to the density of air. And these other coefficients relate to how high above the ground are you, and at what altitude are you above sea level. And of course, V is the velocity. Now that's an important thing to note, that V, notice we're pounds per square foot. So this is like a force equation, and it's pounds per square foot, or pressure. And this pressure is proportional to the square of the velocity. And if you think about the modules themselves, the sunlight, the power that's produced by them is proportional to linearly proportional to the intensity of the sunlight shining on them. So this twice the wind speed is 4 times the force. And that's why if you're looking at 175 mile an hour wind speed in Miami versus 114 miles somewhere in middle of the country, Miami is going to have roughly double the wind forces, depending, again, they depend on location on the roof and so forth as well. So let's keep going here. Oops, I'm going backwards, forward. This QZ is pounds per square foot, but it's really has another factor that's included, and that is how high off the ground, and that's the KZ factor. So once you know how high you off the ground, and if you've applied the KZ factor, then you can calculate a QH factor. And the QH is simply what you get when you enter the KZ factor for the height off the ground where your system is going to be. So that's what QH, it's just QZ evaluated at a certain altitude or height above ground. KD is depends on the shape of the building. For the most part, it's 0.85. We're going to go into some detail on that. GCP is a pressure coefficient. Gamma E and gamma A are additional coefficients depending on the area of the array and how close to the edge it is. Okay, so and here's a definition here, which I think pretty well coincides with what I just said. And like I say, the goal here is for you to know where to find out, how to find out where to look out to get it right. But at least have some understanding of what all these quantities are that you're dealing with. I doubt that anybody who's never done a wind load calculation before is going to be able to just buzz right on out after this webinar and do a quick wind load calculation, but it should get you on track. And get yourself a copy of ASCE 722 and read it carefully. There's a lot of things that could be interpreted more than one way. It's almost like the National Electrical Code. So you need to make sure that you're interpreting it properly. All right, and this particular procedure is valid for all roof slopes with modules parallel to the roof and less than 10 inches above the roof, and a minimum gap between them of 1/4 of an inch if there's more than 2 in a row. Okay, so there are certain conditions under which these can be used, and others you have to find a different way to do it if you don't meet these conditions. So how do you determine KZ? You just look it up. All right, and here's a table for you, and we're not going to spend a lot of time. As you go higher off the ground, K sub Z goes bigger, but exposure B, KZ is smaller than exposure D, exactly as we would expect, because exposure C is, you have to make sure that when you design to exposure C, it's a more robust design. Because exposure C, the wind is, no, remember, this is exposure C, not category C of building. So the exposure we have to define, and that's exposure B is basically a residential area where there's a lot of things that slow down the wind. Exposure C is where there are areas where the wind does not get slowed down as much, or in Florida, any hurricane county is automatically exposure C, whether you got trees or not. And exposure D is if you have a very broad, flat expanse of land or water, then the wind can really whip up along one of those. And so there is more wind there. Okay, so there's your case of Z. You evaluate it, and then you can, in the process, once you get case of Z evaluated, you can, well, here's your exposures right here. I'm sorry, I meant to do the exposure thing first. B is sheltered. C is, again, gotta make sure everything is counted, and there's only 3 categories, B, C, and D. So if you have these unobstructed flat areas, then it's D. And if you're sheltered in a neighborhood or downtown, you're B. But if you're neither, whatever that means, but it's if you're don't have a lot of stuff around, then C applies. Or if you live in Broward or Dade County in Florida, then C applies no matter what. All right, so there's the exposure categories that are used in a determining case of Z. So now we can figure out what KZN is and a few other things, okay? We can also look up the exposure coefficient, the GCP. And these are important because these did vary for each zone and each slope and each roof type. And for example, if we have a roof that's a hip roof, like what we're looking at, that's the one we are designing on. And if it has slope between 7 and 20 degrees, and ours happens to be a 412, which is 18 degrees or so, 18.4, and exposure B, then you can look up on a table. It's not exactly a table, it's a little graph. That in zone 1, your positive pressure coefficient is 0.6. So actually, the downward pressure, I've got a wrong answer here. That -5 is a typo that I missed when I proofread this thing. That would be -1.5. So put a big X on that when you get that slide and fix that thing. I'm sorry, I have to fix that. I don't know how many times I've gone over this to make sure I got all the numbers right. And I'm sure I pressed the key and I just didn't press it hard enough. Anyway, take note, -5 is totally wrong. -2.1 and -2.3, those are good numbers. Notice the downward pressure is the same for all roof zones. Phone is ringing more than usual today. Okay, so there's the exposure coefficients, and they're very specific to the zones and the slope and the type of roof. KZT is a terrain factor, and you have to look at a picture to figure out what that is, but if it's flat, it's equal to 1. Okay, KD, for any normal-like shaped thing, like a house, which some of which you wonder if they're really normally shaped or not. But in any case, you can almost always use case of D equals 0.85. If the altitude is less than 1,000 feet, this is an exponential function, and the 722 actually gives you the formula with all the coefficients and so forth. But it doesn't start going down until at any reasonable rate until you reach about 1,000-foot altitude. And that covers a lot of the country where you can just use it as 1. If you really want to get fussy, you go to the exponent and you calculate e to the x, whatever. And like at 5,000 feet or 18,000 feet is 0.5, something like that, because the pressure, the density of the air is only cuts by half every 18,000 feet or something like that. Okay, anyway, if the height of the roof is less than 30 feet, and if the exposure is B, then K sub Z is 0.7. And since the slope is more than 7 degrees, gamma sub E, that edge factor is 1. Since the area and since the modules are parallel to the roof, 18 square foot makes gamma sub A equal 7. And using the 115 mile an hour wind speed gives QH gamma A equals 16.6 pounds per square foot. And that's what we're looking for. Okay, now this gamma sub A is an interesting thing in itself because let's look at G sub P and some of these things. See, this exposure coefficient, GCP, this is the graph for the roof slope 7 to 20 and zones 1, 2, and 3, and hip roof. And notice here we can get the number that I got wrong for GCP. The blue thing is the downward pressure. And notice that's positive, and that's at minus 0.7 up to 10 square feet effective area. And that effective area is an interesting quantity we're going to look at. And then as the area gets bigger, in other words, as the array gets larger, the effective area gets larger and the downward pressure is distributed over more modules and it actually decreases. And that same thing happens between 10 square feet and 100 square feet with almost every GCP coefficient table, whether it's for 0 to 7 degrees, 7 to 20 degrees, 20 to 45 degrees, or whatever. Your graph is going to look something like this. It's just that the starting points and the ending points are different. So this is the graph where you would get the GCP. And this is the conditions, zone 1, 2, 3, zone 1, zone 2, zone 3 up here. And here's the definition of effective area A. And again, this is one of those where you read it 10 times and try to figure out what they really mean. And that's why I'm saying you don't get this lightly. You want to make sure, if you're really not sure what effective wind area means, then you can go the conservative route and use a value at A of A equals 10. And because that's the maximum value, anything 10 or less. But if you want to go to definition and figure out exactly what it means, then what it says is it's very likely if you've got a nice long string of modules that are not spaced more than 3/4 of an inch apart, but they are at least 1/4 of an inch apart, which they have to be, otherwise you can't fasten them down, then chances are you might get up into that 100 square foot range. And as you can see in zone 3, if you have 100 square feet in zone 3, which is pretty rare for residential, but not necessarily rare for a larger system, that makes a significant difference. It's dropping you down from 2.246 down to 1.4. That's a pretty significant difference. Anyway, these are the things that come into the calculation, okay? And so then you just multiply together, and you multiply all that 16.6 that we just gathered by the GCP numbers, and we're looking at pressures. The worst case pressure here is 38.8 upward lift in zone 3. All right, that's our conservative approach. And that uses A is equal to 18 square feet per module. But here's a little note that I made about A. It could, in fact, be L squared over 3, and it could give A of 92 square feet for the array that we have, the smaller, shorter row. But it depends on how confident you are with that. Anyway, here's then forces on the modules. You got your mounting rails, you put some mounting feet up, and then you figure out how much force have you got for each one of those brown dots, because obviously pounds per square foot times square feet gives you pounds, and then you have pounds per attachment, And hopefully we can put on attachment that won't pull out if the uplift is too much. So at the attachment points, with an 18 square foot module, you can figure out you've got total uplift in top row of 2592 pounds, 3676 in the middle row, 6071 in the bottom row. And so then we just take a look at how many attachments have we got. 11 in the top, so that's 236 each. 17 in the middle is 216, and 21 in the bottom, 289 pounds each. That's not half bad. And why is that not half bad? Because if you look at lumbers, if you're using 5/16 lag screws, which are commonly used, then what we get for the lag screw withdrawal loads, if you've got southern yellow pine trusses, which any high wind load area will typically have, and 5/16 inch screw, you get 332 pounds per inch of penetration into the truss. So if we go back and look there, we got 289 pounds is the worst case, and 1 inch of southern yellow pine with one screw of 5/16 gives you 32. And some of the attachments have more than 2 screws that will go in. So it is possible with most a lot of the attachments have withdrawal loads of 1,000 pounds or more. But you just need to look up the manufacturer's specs. So in any case, that's it for the structural part. And now we can take a look at the mechanical part, and let's take a look at the time as well. See how we're doing. It's 3:17. Okay, we've got 45 minutes essentially. So let's take a look at some systems here. We're going to do a microinverter system, a power optimizer system, and a string inverter system, okay? And every single one of them has got maximum power point tracking somewhere or other. And they also have rapid shutdown. All right, let's do first talk about some general requirements for inverters. All right, you have to have good waveform. If it's not a good sine wave, it kind of messes up what's on the utility line. So good sine wave is defined as less than 5% total harmonic distortion. Some of you know what that means. Not everybody does. Right now, all you need to know is it's listed to UL 1741 and it meets all these requirements. Have to have disconnects on the inverter. And it had the disconnect. This is a programmable type disconnect that says the inverter itself would disconnect from the utility if the utility is over or under voltage or over or under frequency. All right, so this is automatic disconnect. I probably could have said automatic disconnect rather than just disconnect. But in any case, that's what it means. They have anti-islanding requirements because if the utility goes down, and if my inverter at my house keeps feeding electricity to the utility, then your inverter at your house, who's across the street on St. Transform, is probably going to be convinced by my inverter that the utility is still there. And you can imagine what would happen is that you get a bunch of inverters. So this anti-islanding requirement says that they have to be designed so that if the utility goes down, they lose their synchronization and they can't fool another inverter into thinking they're the utility. And that's really important. It's very clever, and the design on that is very interesting. And part of the reason that can happen is because they're designed as current sources synchronized by a utility voltage. Okay, and then a lot of them will have an option for utility control to provide grid support. If you've got a big, excuse me, if you've got a big utility PV system, say 200, 300 megawatts, last thing you want is for that thing to shut off if the utility is having trouble meeting its demand. So that's got to be allowed to ride through and to help the utility to meet its demand. And so therefore, you can make arrangements with utilities within any of the modern inverters to provide grid support if the grid voltage starts dropping too low or if the grid frequency starts dropping too low. What otherwise would require a disconnect now can allow for the PV to stay on to try to keep and prevent the grid from going down completely. Okay, so let's design a microinverter system. Boy, that was quick. Here we go. Oh, we looked at this before. Okay, so we already know what's there. So what are the rules? Have to match the microinverter to the module. Module has certain open circuit voltage and short circuit current, and the microinverter has to handle them. Okay, straightforward. We'll do that. Some inverters are you're not supposed to have more than 60 cells in your module. One cell will typically have an open circuit voltage in the neighborhood of 0.6, so 60 cells is going to be somewhere in the neighborhood of 3640 volts or so. And others will do the 72 cell module, which has sometimes an open circuit voltage close to 50. So you just need to look at the specifications on the microinverter, make sure it matches up with the module itself. Okay, and here's some more data. And again, these are things. What am I got for time? I'm not going to read every word of these design rules because the intent here is for you to know that they're here and they're straightforward. And if you're really interested, you come back and look at them again. Okay, but now we're going to apply these design rules. We're going to take a 400-watt module that's characterized with the following properties. We're going to take the 290-watt microinverter and see if it'll work. So look at the yellow. Open circuit voltage on the module is 49.8, maximum DC input 60. Well, on a cold day, that open circuit voltage could go as high as 55, but it's still well within the 60 volt limit, so the yellow match is okay. Also, the low temperature open circuit voltage could go 56. So yeah, that's fine. We're good. 60 makes it just fine. If we look at the white one, the short circuit current, how does that match up? Well, 10.36 for the module, and the microinverter allows 15, so we're good there too. The module has an output power or maybe of 400 watts, and the module rated power range is 235 to 440, so the microinverter is happy with that as well. The weighted efficiency, meaning the efficiency of the microinverter under a range of different temperature and sunlight conditions, is 97%. And the only important thing here is the DC from the module to the microinverter cannot be grounded. It has to be an ungrounded system up there. Okay, and that's because of the non-transformer. There are no transformers in microinverters, and the AC output is connected to the grid, which has a ground associated with it. So therefore, you can't. What it does is messes up the microinverter if you have the grounded array. So once upon a time, generally the negative lead of the power coming down from an array was grounded, but that's not done anymore. Routinely, it has to be not grounded. And in commissioning, you want to check and make sure that neither the positive nor the negative lead is grounded. Time to another drink of water. Okay, so we've got a matched module and microinverter. So now we select the rest of the components. We got the module, we got the microinverter. The circuits are going to be 20 amp circuits because the manufacturer of the microinverter provides the wiring harness to do that. It's open wiring up underneath the modules. No conduits or anything up there. Just the wires are hanging loose open with wiring that's rated for very heavy duty insulation on them, type PV. And as long as it's properly supported under the modules, it's fine. So microinverter, we're using microinverters to 1.21 maximum output current. So to stay less than 16 for amps total for a 20 amp circuit, because we need to have the wire at 120, the circuit wiring and overcurrent protection has to be at 125% of the total maximum output current from the string of modules. That means you can't have more than 13 in a circuit. Very straightforward. Simply divide 16 by the output current of 1, and that means you can have 13 of them. So here's our system that we laid out previously, and we can have we've got 24 modules here. So we can have 12 modules each, and that'll work just fine because we can't have more than 13. We could have 13 and 11 if we wanted, and that would still add up to 24, because each microinverter is its separate inverter that's totally independent of the operation of the other ones, other than under a rapid shutdown command where they all had to shut down. All right, so we can do 2 circuits with 12 modules each if we do it like this, maybe. And that'd be the first circuit, and then here's our final circuit here with 12 modules. And that adds up to 14.52 amps per circuit, well within the 16 amp requirement. The array itself is 9,600 watts DC. And you'd look at this roof size, and this is a fairly typical residential roof. So if one residential roof section can do this, that's not bad, because in fact, the average house can make all the electricity it needs with a 9,600 watt array. If it has properly designed with energy efficient appliances and so forth. It's listed to, the microinverter has cabling that provided by the manufacturer. Circuits are fed to a combiner box at the ground level by way of conduit, because there's a junction box on the roof where the open wiring is converted to wiring in a conduit. And that's that. So once you get down to the ground, you're going to have something like this, a combiner box with circuits coming down from the roof. And these 20 amp breakers, by the way, are 2-pole 20 amp. We've got single line diagram here. There may or may not be an unfused disconnect, depends on the size of the system. If it's over 10,000 or over about 12,000 watts DC rating, or over 10,000 watts AC rating, then you need an external, easily accessible unfused disconnect that the utility has access to. Otherwise, the disconnect has to be accessible, according to that definition. So this is part of it, and then the next thing we go to is to the point of utility connection, and that can look a number of different ways. Wait a minute, I'm going backwards here. It might look like this. It might just backfeed a 40 amp circuit breaker in the main distribution panel. And the rules for that are straightforward. NEC 705-12B32. This is called the 120% rule. And it says that the sum of 125% of the inverter outputs, that's the 36.3, plus the rating of the bus bar. I'm sorry, plus the rating of the main circuit breaker, the 200 amp, must be less than 100% of the rating of the main bus bar. Well, 120% of 200 is 240, and 236.3 is less than 240, so we're good. So this is an okay way to do the interconnect. Okay, and all the circuits come down from the PV inverters are 240 volts AC. There are 208 volt AC outputs available in microinverters. If you happen to have a 208-volt system, they're a special order, a different model. Okay. If the 120% rule doesn't work for this thing, we can do a thing called a line side tap. Start with what came down the last time, but this time, if the PV plus the main circuit breaker is more than 100% of the bus bar rating, or if there's no room in the main distribution panel for that backfed circuit breaker, then you can use the thing called a supply side tap, which means we can tap onto the supply wires to the main circuit breaker like this. So you've got the wires from the utility meter go to the main circuit breaker in the distribution panel, and you can connect using a fuse disconnect, 40 amp fuse disconnect in this case, less than 10 feet away from where that tap is. And you've met the constraints of 705.11. Now, there are some cases, though, where you can't get in there. That 150 amp is in an enclosure that includes a meter and some bus bars and distribution capability for circuit breakers. So you just can't get there. So what do you do if you can't do this line side tap? Well, of course, there's a solution to that. And why would I have asked the question if there weren't a solution? So here we go again, but now we're going to do it like this. We're going to use 705.12B33. And notice what's happening here. We put an extra 150 amp circuit breaker. That extra 150 amp circuit breaker means that the tap is in between those two circuit breakers. And yeah, if we have some electrical engineers, this is a perfect example of applying Kirchhoff's current law. And I knew that you heard that, you'd be thrilled and absolutely want to eat all your dinner tonight and the dessert besides. That you had a sense you could tell all your friends you heard about Kirchhoff's current law and you're in this webinar today. And so what's the deal? Why is this? Well, for one thing, the 150 amp on that the main distribution panel says that no more than 150 amps can go there, no matter where it comes from utility or otherwise. So that says the utility is there, but you just have two options for feeding those loads. You can either feed them, and in fact, sometimes both of them will be working. You've got 150 and the utility is there and the PV is there. And so the first choice is from the PV and whatever's left over comes from the utility. If the utility, if the loads on that panel don't require all that PV current, then it can go up to that circuit breaker on top. But you can't have more than 150 amps going out either. But then that's not a big deal because the PV itself only has 40 amps maximum that's going to go out. So when we're backfeeding to the utility, then it's not a big issue anyway. So those two, you could actually have then a couple of circuits between those two. And as long as the sum total of the overcurrent protection for the loads plus the source does not exceed the rating of the bus bar, then you're okay. And that doesn't include the rating of the 150 amp. Now, you have to read that several times to realize exactly what it means. And again, I'm showing what the options are. And this doesn't register exactly out front, you have to have, you'll simply need to take another look at it. Okay? In that case, they limit the current. And here's the point about the special. If there are loads connected between the two circuit breakers, there can be some, but there's just a limit to the amount. And that's pretty clearly defined. So now we can design an optimizer system. How much time do we have left to design it? We should be able to get that one in. Notice the difference. Optimizers are DC to DC converters. DC in, DC out. Notice they are connected in series. And the nice thing about an optimizer, the reason it's called an optimizer is because it has its own maximum power point tracking, which says it will make sure that that module is operating at maximum power. And what it will do is adjust its voltage and current such that its current will be exactly the same as the current on all the other optimizers in that circuit, but its voltage may be different. And it's very simple. P is equal to I times V. Power is equal to current times voltage. So the more power that's delivered to any one optimizer, the higher its voltage goes. Okay, so what are the rules on this? Well, for one thing, here's what I just said. I guess I kind of jumped the gun, but in any case, the optimizers are controlled by the inverter, because if you see, we have two strings of them here, and they're two series strings. And that means the voltage coming out of each of those two strings has to be the same. And the inverter is going to tell these optimizers what it should be. And they are going to adjust accordingly. They're going to adjust their currents accordingly. So the voltages will, based on the amount of power coming in, will adjust accordingly as well. So here's our rules. Only 4. This is very simple. 4 rules. Optimizers must be matched to the module. Obviously, okay, fine, we'll do that. Manufacturers are very good at following and making stuff that other manufacturers need. Circuits may have different numbers of modules. Why is that? Very simple, because these things are maximum power trackers. And what happens is, in order to maintain balance at the string level and the same voltage, the strings will adjust their currents, but you add up all the powers of all the optimizers in the string and divide them by the voltage that the inverter is telling them to operate at, and that tells you the string current. And it's just that simple. So you do that same thing for every single string, and that tells the optimizers what voltages they have to operate at in order to produce the amount of current that's necessary to operate at just the right. It's a very interesting control algorithm, let's put it that way. And it's really neat to think about how that works. What's even more fun is to develop a spreadsheet that uses that formula and then start cranking in different values of optimizers, because with optimizers, there is a minimum number of optimizers you can have in a string, and there's a maximum number you can have in a string, just as is the case for microinverters. Okay, and the main thing is that the total array rated power should not exceed 155% of the inverter's rating itself. That means if most of the time the modules don't operate anywhere near even 80% of their rated power, because they get hot and clouds are coming over, the sun's not shining directly, whatever the case. But it doesn't mean they don't put out the promised annual kilowatt hours. That's what we're paying for here. And so there's a limit to the total power of the array, because there's a limit to the amount of control function. The control functions of the inverter have limits of voltage and current. All right, so we can look at some of the matching here like we did with the other circuit. And here's a match between a particular optimizer that will do everything the module needs for it to do. And if you have a bigger module, you need a bigger optimizer, one that has, can handle higher voltages or currents or whatever. Again, let's don't do all the numbers. Those who seriously want to do this, download the slides and you get a chance to look at them and compare. You select the inverter and you select the circuit length. So let's see what that does. Array plus optimizers. The array, we already know, is 9,600 watts, okay? So if the power in for the optimizer is 400 watts, then the output voltage is going to, and if V out, what do I say? Optimizer V out. What is the optimizer output voltage? If optimizer input power is 400 watts, then the output current, or it's 15 amps. Well, then the voltage is going to be 26.7 volts, simple. Voltage equals power divided by current. And the maximum current that optimizer is going to output is 15 amps. All right, so that's a good thing to know. If the output current is less than 15, then the output voltage has to be greater than 26.7 in order to produce that 400 watts at the output of the optimizer. But there's a limit. The optimizer can't go over. The inverter limit says you can't have more than okay, the 400 divided by 26.7 volts. That's 15. So you can't have more than 15 optimizers. Otherwise, at maximum current, it's going to overload the thing. 24 modules, turf circuits of 12, 7,600 watts at 400 volts, 15 amps. That leaves 6,000 watts for, this is the inverter, is a 7,600 watt inverter. Okay, and then the inverter, this is, I'm sorry, this is not, oh, the maximum input power is 11,800 watts. That's DC. That's not the output power. You can have an 11,800 watt array. The DC to AC ratio is still acceptable. And the reason is because the actual power in is almost never going to go very much over 7,600 watts, less than 1% of the time. And on that time, the inverter simply does current limiting. All right, maximum input voltage 480. So from all these things, you can determine the length of the string, the maximum and the minimum number of modules. So the nice thing is the modules can be different and be oriented in different ways. The minimum string length is 7. The maximum string length is 15, so you can have anywhere between 7 and 15 in a string for however many strings that you have. And they're still all going to operate at maximum power as long as the strings are in length between somewhere between 7 and 15. Okay, so how would we do that? Well, same modules with 15 stuff, so we can do 13 and 11 this time. So here's our 13, and here's our 11. 400 volts per circuit, 9,600 watt rating. And there it is. What do you do at the ground? Same thing. All depends on what you've got. But you've got your 705.12 B31, B32, and B33 that we can use. Okay, so or 705.11 on this one. And there are some other options too that we're not even talking about today, but we could be used if we had to. We've talked about DC to AC ratio. Here's a curve showing that indeed with a DC to AC ratio of a 1.5, you're still essentially getting out the rated power rating, the annual kilowatt hours. This is a simulation that for different DC to AC ratios. And that's one of the things you enter into the simulation. And so that's why you'll see this a lot. And you'd see, gee whiz, I've got a 7,600 watt inverter and a 10,000 watt array. What am I going to do with that extra 2,400 watts? Well, the answer is they're probably not going to be there in the first place. And even if they were, it wouldn't be much over 7,600 watts, and it wouldn't be over for very long. And the inverter simply blocks it and says, no, we're going to stop here and wait till the sun gets a little darker or something. Okay, so these are annual outputs for the 290 watt microinverters connected to different modules. So it's the power in that makes the difference on 290 watt. Yeah, the DC to AC ratio, they still put out pretty much the same. So it's the DC input power that really determines your annual output. Your DC module rating. I mean, sure, the AC output power that makes, but the AC module rating is the thing you can do your simulation from and get a very reliable simulation. Sorry, I said AC, I meant DC. I guess it's getting late, isn't it? Time is it anyway? 3:45, that's not too bad. All right, so here we have two different systems. We've got a this is Orlando, by the way, and again, I encourage, NREL SAM is very intuitive. And it's downloadable for free. You have to give them your email because then they tell the government that this many people are using SAM, therefore you should keep funding us. So that's the only thing they use their email for. I've never gotten a bunch of emails from NREL saying you want to buy this, you want to buy that. Every time they do an upgrade, they'll let you know there's an upgrade and you can download it for free. So don't be afraid of NREL. They're good people. All right, so if the maximum power point tracking is at the inverters, that's a different story. Because then we've got it's being done at the string level. And if you do maximum power point tracking at the string level, that means if the strings are connected in DC in series, as we discussed earlier, if one module is shaded, it's going to change the power output. So if you've got, you can't do with straight inverter level design with the maximum power point level at the inverter, you can't do what you can do with optimizers and with microinverters. You can't put modules facing in different directions and have them in the same string. You can do that with microinverters and with optimizers, and they optimize individually their output, and they don't affect each other. But modules do affect each other if you don't have these cute little boxes in between. All right, so that's the reason that you got to be really careful. That doesn't mean you can't do string inverter designs. You can do them as long as all of the modules in each string are facing in the same direction at the same tilt. In other words, the same orientation. Then it's fine. But if they don't, then you need to break them into different strings because every string has to have all the modules in every string have to have the same orientation, but all strings don't necessarily have to have the same orientation as long as you have a separate maximum power point tracking input for each string. And it's just that simple. And the other thing about the source circuit design is when they get cold, the open circuit voltage goes up, and when they get warm, the maximum power point voltage goes down. And you got to make sure that the number of modules in the string does not exceed the rating of the input voltage of the inverter, or you can actually do physical damage to the inverter. And if there are too few modules in the string, and the output voltage drops below the minimum inverter rated maximum power voltage, then you're affecting the optimization of the maximum power output of the string. So this can sometimes be pretty seriously constraining to the maximum and minimum numbers. And let's take a look. Let's do the math here. Again, we got our same friend, the same module, and we're going to look at voltage extremes, okay? And if the inverter input range is 205 to 600, then the coldest temperature is minus 20 C, then the temperature difference between the standard test conditions and minus 20 C is 45 degrees because the modules are tested at 25 degrees C. The open circuit voltage increases by this formula and it goes up to 56.1. That's okay. But if we know that, then the maximum voltage, 600 divided by 56.1, says you can't have more than 10.7 modules. And that says you better cut it back to 10 because 10.7 11 will give you more than 600. So you have to round down on this. So that means your maximum string number of modules is 11. Sorry, 10, 10, 10, 10, not 11. Sorry. So now let's look at the minimum. That's determined by the high temperature and the effect on the maximum power current. And the hottest temperature might very well be 65 C. Okay. From the sun shining on the modules. Okay. It's not going to be 65 outside, but the module can get up to 65 using this formula right here, starting with the ambient maximum temperature. And if the temperature difference, if it's really at 65, then you got 40-degree temperature difference, means your maximum power voltage will drop to 34.9. 245 divided by 34.9 is 7.02. So you better have 8 of them, because 7.02 is marginally close to that low level. You can do 7, but 8 is a little more comfortable. So that says, gosh, 7 and 10 modules. That's a lot different from what we're looking at in these other circuits. So this is something you need to think of if you want to get rid of the cost of either the optimizers or the microinverters. Is can you lay your system out with groups with strings between 7 and 10? And if you're between 7 and 10, well, let's see what it does to the circuit we're trying to do here. Turns out with 24 modules, we have to do 3 times 8. We could do one with 7, 8, one with 8, and one with 9, but to do that, we'd have to have 3 maximum power point tracking inputs. We may or may not be able to have it. It depends on the inverter. Okay. So anyway, let's do it the simple way with 3 of 8 and see what that does for us. Okay. And what's that going to look like? Oh, well, what it's going to look like is that it's going to work. All right. I was thinking I would see one of those circuits, but the whole point is all those circuits that we showed for connecting to the utility, they're all the same. They don't care what's up on the roof. The inverters, once you're at the inverter, once you're at AC, then you've got the same situation for not overloading any circuits, not blowing any circuit breakers, protecting all the equipment and so forth. So therefore, it is important to include a compatible rapid shutdown system. And, you know, I would say right now, what's out there for residential installations is less than 10% are going to be this kind. But this is what's out there when you have a large commercial industrial utility system, the multi-megawatt systems, because all the modules are facing the same direction. They're all getting the same sunlight exposure. So in those cases, these are the steps you have to go through to make sure that your string lengths are acceptable to the module or the inverter parameters. So guess what? We made it. I've been watching to see if there are any Q's and A's out there. I haven't seen any lighting up. That means either I put everybody to sleep, or nobody had any questions that was explained perfectly, or nobody understood anything and they don't know where to start from in answering any questions. But what I'd like to do is ask a question that we wanted to do at the beginning is I'd like to see who the participants are here. And I see we got Michael, Robert, Sharif, Stephen, and Thomas, Stephen B and Stephen M. Where's everybody from? Michael, how about you? Can you turn on your mic and just tell us what kind of engineering you do and whether you have any solar involvement? And the rest of others, we'll just have your mics ready to turn on quickly and give a quick rundown. Just we'll get to know each other a little bit here and know what we do. No, let's see, while Mike is looking for, how to turn on his microphone, how about Robert, can you, unmute and, just tell us what's your engineering background and what are you doing right now? I mean, you're sitting and watch your computer, but I mean, what's your current job function? What happened? Oh, I don't see, okay, you work for like a utility in Omaha, mechanical engineer background, okay. Um, all right, then, if you don't have that option to unmute, I think they're in different places on different screens, so go ahead, just type in the chat box then, let's use the chat. And that way we don't have to worry about anybody else talking when somebody else is talking, you just type in. You just tell us, are you electrical, mechanical, structural, whatever? Okay, mechanical, civil for a 40 home, that's good, that must be very satisfying to be doing that kind of work. Steve McQueen, PV connectors and harnesses and farms across the country, fantastic. Solar PV for apartment buildings in Wisconsin, okay, all right, that must be fun too, working with apartment buildings. Wow, yeah, well, of course, apartments have one owner, so they can decide that it's worth their while. Try it for a condo someday. One nightmare. Civil, working on remote water and wastewater systems, often powered by PV. Yeah, that's good. Yeah, that's a great way to power wastewater systems. Do you have battery backup, I imagine? Yeah, sure, you'd have to have. Small jobs for residential, right, okay. Great, so have we covered them all? I see I'm at the bottom. I see, you don't have a mic switch. The reason is because that was under the control of the host. That explains it. Okay, anyway, uh, nice to see the difference in disciplines. I hope everybody learned something today. And I hope you all have a great evening and a good week and good summer. And I believe we're just about at the end here. Yes, we are. This is why I'm still working at age 80. Young man on the right is now a mechanical engineer. The young lady on the left has a graduate degree, or not a graduate degree, has a degree in communications. Is living in Oklahoma. And Danny is living in Eden Prairie, Minnesota. And my great grandson is the son of the young lady on the left. About 21 years later than this picture was taken. Okay, so yeah, good reason for doing any of this kind of stuff is for future generations, and that's certainly why I wouldn't be sitting here at this computer this afternoon if I didn't think it was important. So thank you for coming, and Mr. Host, you can sign us all out.
I see John's in Broward. You send them the